Hello there, welcome to a presentation which is going to introduce you to an approach of solving ordinary differential equations of order n. But in this presentation, we're going to like to exploit what we know in the approach of solving first order linear equation and see whether we can find an approach which is more of algebraic to solve equations of order n. So starting from where we are familiar, let's look at this more carefully. Recall that with first order linear equation of this form, and we solved it using the integration factor. But note that this equation, you can simplify it and take it in the simplest form this way, where p is a constant number, say m, and the right hand side of this equation q, which I denoted here as f of x, can be any function, polynomial function, trigonometric function, exponential, or any combination of the above. So looking at this more closely, we could, first of all, in general, what we want to do, we want to be able to solve equations of this form of order n, parting from the method of solving a first order linear equation of this nature, which already I've said we can simplify in this form to write it in this form where our p of x is a constant function m. So m here is a constant. So let's take an example for this. Let's say we're given a simple linear equation like dy dx plus 2y equals to 0. In this case, we set q equal to 0 to get this homogeneous equation. So what I said is that we want to use, first of all, look at the linear method and then relook at this thing and see whether we can get an algebraic method to solving it without really involving the integration factor. Using the integration factor here, what do we do? We simply identified our p, in this case, which we've identified is equals to m, a constant. And then, lastly, what you identify is q, and q of x is also a constant 0 for this case. And for r, we need to get it from this integration, which tells us that r is e to the power of the integral of p. In this case, our p is 2, and then we're integrating 2 there, and we are saying that our m here is equal to 2. That is looking at this and that where q is equal to 0. So this would simply give us e to the power 2x. That would be our integration factor. And then what we know is that the product of the integration factor and the y is equal to the integral of q times the integration factor, which is e to the power 2x with respect to x. But then it is telling us that we are integrating 0. Now we can write this way. Now if we know that when we're integrating in this fashion, we're simply looking to raise the function which differentiates to 0, which we all know in this case it will be a constant function, let's say c. And now from this we get that e to the power of 2xy is equal to c, which will land us at the fact that y is equal to c times e to the power minus 2x. So what I want to call your attention to here is that just look at how this 2 has actually migrated from here to this kind of position, and finally in the solution. That's what exactly we want to take advantage of. We want to be able to arrive at this situation in an algebraic fashion. So what I'm going to do here, now let's consider this very equation, and here what I would like to call attention to is that let's set, now we're setting dx equals to some parameter. Let's say in this case, let's call it m. In this case here, what we should understand here in dy dx, we've got two things here. We've got dx and y. we're writing this way. In this case, when I'm writing this way, I'm saying this operator here, we call that differential operator. Differential operator. So this is the differential operator. So in this case, as if this is in the equation, they say the differential operator is applied to y. So what I've done here, I said let's set d dx, the differential operator, equals to m. If we do that, rewriting this equation would simply say d dx multiplied should have applied to y plus, and in this case here, 2y. And strictly speaking here, what we would say this is a differential operator of order 1, and this would be exactly the same thing as writing as a differential operator of order 1 applied to y plus 2, and here the function y is not differentiated. You can as well consider that a differential operator of order 0 is applied to y, and then we would say this is equals to 0. So doing this way, check what after setting d dx equals to m, what you can write here, you can simply write this as my plus 2y, and then moving to this kind of version, you can say my, which is my m to the power 1 plus 2 m to the power 0 y equals to 0. But we can take you can sort of do some kind of similarity. What we have here, we have y not differentiated. So in other words, if we take d dx as a differential operator, dx of order 0 is same thing as the identity operator. In this case, you don't actually change y, you just leave y as it is. So this equation can be written as simple my plus 2. So 1 times, if this is identity, like 1 is an identity for multiplication, 1 times y would be equals to y. So we can take that, interpret that thing there as 1 times y, and this y, so we got here 2y is equals to 0. So when we look at this, we can see that we are simply in the presence of a kind of equation which you can manipulate algebraically this way. We have here m plus 2, and the y here is a common factor, and that is equals to 0. And we all know that if you've got such a situation, this would imply that m plus 2 equal to 0, or y is equal to 0. But saying y is equal to 0 was saying that the solution to this equation is equal to 0. But we can't set ourselves on a task of finding a solution which is 0. We call this a trivial solution. This is a trivial solution, and it's clear to anyone that if you substitute y here, differentiate y here, y which is 0 gets 0, and the 2 times 0 gets 0, this equation will be satisfied. So our task here is to find a non-trivial solution. So here we expect y to be a non-trivial solution. So with that, So expecting y to be a non-trivial solution here, then we can say now here, let us say y is non-zero, meaning it's non-trivial. So if y is non-zero, the only case remaining is that m plus 2 is equal to 0 from this kind of discussion. And this equation, we're going to call this the characteristic equation of the differential equation given there. And then note that if we solve this characteristic equation, we arrived at the fact that m is equals to minus 2, which we see that this minus 2 is actually the same number which appeared there, minus 2. And here it sits here as a solution to the characteristic equation. So here this is solution to characteristic equation. I'm going to denote that in short, ch dot eqn. So it's solution to characteristic equation. So which means what we can do now, we can actually build up that solution by simply saying y equals to an undetermined coefficient c, which is a constant which we know it comes from there, multiplied by e to the power minus 2x. In short, what I'm trying to show you here is that to arrive at this solution which you underlined here, we can actually have two approaches. One, we take the equation as it is here, we identify a differential operator with the parameter m, like we did here, then write, instead of writing dy, and write my plus 2y, knowing that the differential operator is over order 1, and the order 1 is simply the identity operator which leaves y, and then that lending us to a characteristic equation like this. So which means now the method of solving this problem translates to another approach, which is as follows. First, number one, looking at the equation carefully and extracting a characteristic equation, which would be m for the d operator plus m plus 2 equals to 0. So in simple there, we just simple say characteristic equation equals to is m plus 2 equals to 0. Then the number 2 approach, solve this equation. After solving the equation, then simply build up the solution like this. Let me look at another example, this one. Let's say now with dy dx minus 3y equals to 0. According to what we've said there, we're going to set dx equals to m. So now the initial step in this case, according to what I've just said, would be to extract the characteristic equation. So I say initial step ch eq n for characteristic equation. That would be m minus 3 equals to 0. And then solving this equation would say, therefore, now solving this equation would say here, therefore, m is equals to 3. And then building the solution, we would simply now say our y, in this case, is a general solution because we're using here an undetermined coefficient c. Y general will be c times e to the power 3. Now, so power 3x. So then now we simply need to relook at this equation and see whether we can do it using the first order approach and get exactly the same thing. What we do here, we'll say our p is equals to minus 3. I hope you can see that this equation, to take it to standard linear form, you will say dy dx plus minus 3y equals to 0. Then your p stands out as minus 3. Then our q will be the constant function 0, and then our r would get it by doing the usual integration e to the power integral of p. In this case, this is minus 3 dx, and this gives us e to the power minus 3x. And then coming out, you come here and say y times e to the power minus 3x is equal to the integral of 0 times e to the power minus 3x dx. And again here, like we saw before, we're integrating 0, and we know that 0 is the derivative of a constant, so the right hand side is equal to that. And then we can now, looking at the extreme ends of the equation, dividing both sides by e to the power minus 3x, we get that y is equals to c e to the power 3x, which is exactly what we got there. So this is our y general. Once we've understood this way, so now we can actually look at any equation of order 2, 3, order n greater than 2 in the similar fashion, in such that our first initial step would be to extract the characteristic equation, and then solving the characteristic equation, and then lastly construct the solution using the roots of the characteristic equation, and then we'll be done. So I think our exercise now will be simple to, what I want to show you now is how to get a characteristic equation for equations of different order. Let's do it this way. That's our way here, extracting characteristic equations. First, what I'm going to do, we're going to first of all consider homogeneous equations, and then we're going to look at, later we're going to look at how we manipulate the situation of non-homogeneous equation. So first example here, we said if we had dy dx plus, let's say 2, what we saw before, equals to 0. Our simple understanding should be, next thing is to look at this equation. This one is dy dx, differential operator applied to y, plus 2y equals to 0. And then let dy dx, the differential operator, be looked at as m. And then what we're going to have here, we simply have my plus 2y equal to 0. Then the next thing is to factorize this. M plus 2 times y equals to 0. And usually we will say here this implies that m plus 2 equal to 0, since y is not considered to be a trivial solution. So y is not taken as a trivial solution. So our only possibility that m plus 2 equal to 0. Then this m plus 2 equal to 0 becomes our characteristic equation. We've already seen that we solve this and arrived at m equals to minus 2, then build our solution. That's important. So now let's look at what if this was a second order equation. If we're given a second order equation, for example, like dy dx plus 3 dy dx plus 2y equals to 0. For this case, we'll do something similar. We'll come here and they say d, in this case order 2, applied to y, plus 3, first differential operator, this is the power 1, applied to y, plus 2, here we put the differential operator of order 0, which gives us back the function itself, multiplied by y equals to 0. And then there, what we have to consider now, because if we take d dx as m, now d2 dx to the will be now taken as m squared. So coming here, we simply put m squared y plus 3my plus 2y equals to 0. Then there we'll have m squared plus 3m plus 2 multiplied by y equals to 0, and then which implies here that m squared plus 3m plus 2 is equal to 0. Only that's equal to 0 because our solution y, we take it as non-trivial. Then from what we've seen before, then it would simply tell us that we should solve this equation here, which is this equation there, which we can solve by factorization, and generally would solve in particular we solve by factorization, or we can use also the quadratic formula, which can actually involve different roots, repeated roots, or even and complex roots. So what we want to learn in this in the following presentation is how to handle different equations of this nature. We can even go to equations of order 3, order 4, in this case addressing differential equations of similarly order 3, order 4, and so on. So in this case here, what we do basically, we take m squared plus 3m plus 2 equals to 0. Factorizing this, I think you can see that this is m plus 2 multiplied by m plus 1 equals to 0. Then what we're going to get here, we're going to get that m is equal to minus 2, or m is equal to minus 1. So in this case here, what we're going to do, we're going to actually use these roots to build our solution. I hope the introduction is what we've said here. We've introduced to something very, very important. I reiterate that the process is as given an equation, you transform it in such a way that, or you look at it in such a way that you can extract your characteristic equation. This part of the discussion is a discussion which basically aimed at trying to convince you in terms of this approach. But what we do, we would wish to move direct from the equation straight to the characteristic equation. Then from the characteristic equation, solve, and once we have the solution, then construct the solution. Those are the examples we're going to look at in the next part of our presentation. Otherwise, at this point, I would like to say thank you for listening. Let's meet in the next presentation.